slides then.
Yeah. Okay. All right. So welcome for this first one lecture, one seminar of the academic year. It's really my pleasure to introduce Professor Ahmed Elbanna from the University of Illinois at Urbana-Champaign. Professor Elbanna hails from Egypt. He got 2 degrees from Cairo University, a BS in civil engineering and an MS in structural engineering. After that, he went to Caltech. We also got 2 degrees, an MS in applied mechanics and a PhD in civil engineering. He got his PhD in 2011. After that, he spent about 1 year at the University of Santa Barbara in the physics of complex system group, I'm sorry. And then joined the University of Illinois about 3 years ago. So he's a structural engineering by training. He teaches design of steel structures, but his research interest is in the complex phenomena, understanding of complex and modeling of complex phenomena, such as friction and fracture, which has wide application in engineering materials, in biology. Here we see a little picture here with a fracture of bones, and also in geophysical application, and that's the subject of his talk today, is about earthquake rupture. So please join me to welcome.
Thank you very much, Emmanuel, for the kind introduction. It's a really great pleasure to be here in the University of Minnesota and to give this talk in a place where many things we know about geomechanics and poromechanics has come from. So it's a really great honor. I'm going to talk today, as you can see from my brief title, about some phenomena in sheared granular materials with particular application to earthquake ruptures. I'd like to acknowledge my collaborators, Professor Jean Carlson from Santa Barbara Physics, now Dr. Charles Liu, who is a postdoc at Los Alamos and was a graduate student at UC Santa Barbara, and then my Illinois students, Sitara, Shauma, and Koenig, who actually has done work I'm very proud of and I'm going to show you today. So of course, I feel this is very primitive to show in a department which has a long tradition of excellence in geomechanics, but I will show it anyway. So why are we interested in granular materials? We are interested in granular materials because their physics control deformation and failure and phenomena in a wide range of systems, from earthquakes. This is a picture of the famous San Andreas Fault, where actually when the 2 faults move past one another, they actually move by shearing a layer of granular materials that's sandwiched between the 2 sides of the fault. Of course, landslides, pharmaceutical industry, food industry, and complex fluids, all of them are interested or related to granular material and granular mechanics. But as engineers, also granular materials provide a very interesting avenue for discovering new phenomena, new nonlinear dynamics, etc. So granular materials, at least the amorphous part, they have a jamming transition. They could show an amorphous crystal transition. They have rheological transitions from rate strengthening, where the strength of the material can increase with applied rates. So you have a viscous-like behavior, or rate weakening, where the strength of the material decreases with increasing rates. So you have an instability-induced kind of behavior. Of course, nonlinear wave propagation properties, and we have experts here on that field, and reconfigurable structure. I know Stefano loves Lego, so I put that picture. Though we are also interested in disordered Lego. So how would we, if you have a granular material which is disordered, what kind of wave phenomena does that permit? So as I mentioned, the focus that I would like to show today in this presentation is in the behavior of confined sheared granular material, which is very relevant to earthquake mechanics. And the bigger picture is that we eventually would like to model dynamic rupture propagation of earthquakes on fault planes. But to model that, we need to identify the friction law that governs the frictional sliding during the earthquake. And to do that, we need to actually understand what phenomena happens at the grain scale and how they reorganize to lead to shear banding and other complex phenomena within the fault gouge that would eventually control the dynamics of earthquake propagation. And I would like to acknowledge that in the last 30 years, probably, there have been a great experimental progress in understanding behavior of confined granular materials under a wide range of pressure and velocities. And I took this figure from Professor Terry Tallis at Brown. He's one of the godfathers of rock deformation when it comes to earthquakes. And you can see here the slip rates that we are interested in relevant to earthquake phenomena ranges from nanometer per second. That's what the plate tectonics or the plate motion rate is, up to probably few or 10 meters per second. And that's when the earthquake actually becomes fully dynamic. This is how fast the two sides of the fault move relative to one another. But moreover, the range of pressures that are active are humongous because, of course, as the earthquake propagates near the rupture, it encounters lower pressure, but it nucleates at depths like 7 to 10 kilometers, where the pressures are of the order of 300 to 400 megapascal. So really, although we can measure phenomena in granular materials and rocks at low slip rates and high pressure, and we can also measure phenomena at high slip rates, but at low pressure. This is a limitation of how much power our machines can provide. What we are eventually interested in is this friction dream machine, where we can actually test materials in this upper right corner, okay? So this combination of high pressure and velocity is actually what we are after. So there have been some interesting progress, as I mentioned. So recently, Professor Tallis has acquired a machine that will be able to measure properties up to 100 megapascal and add velocities that are a few meters per second. So that's a great breakthrough that we are expecting to happen. But even with that, there are still challenges existing in how you are going. In rocks, it's easier than when you have gouge. When you are testing these granular materials at high pressure, high speed, how you are going to confine the granular material from spalling out of the machine, how to measure, how to control the temperature rise so that it will not melt your machine. The pore pressure confinement and control is very difficult at high slip rates. And furthermore, most of the machines that are capable of applying high pressure and high slip rates are of the rotary shear type. And this rotary shear type, although it's very insightful, but what probably we are more interested in eventually is to understand how the granular material behave in a geometry mimicking dynamic rupture propagation. So we would like to see, say, a direct shear test or a double shear test that accommodates high slip rates and pressure, also high slip distances, so that you can see the interaction with waves and the complexity of shear bands and heterogeneous compaction dilation. So although I don't claim what I'm going to present today would solve these problems, but we think that if we start from a theoretical point of view, a theoretical investigation, by identifying the important or the fundamental mechanisms associated with the granular deformation, we might be able to bridge this gap. And I would like to show you today some of the recent progress that we have been making in that area. So this is just a schematic. We have this granular material confined, and then we would have a crack or a shear band propagating through the granular material. And we'd like to think about how this granular material would deform. And the theory that I'm going to discuss postulates that this granular material, when it deforms, it generates plastic strain. And this plastic strain is not distributed across all the contacts, but is actually concentrated in few sparse contacts that are actively slipping at a given instant of time, and these contacts are continuously formed and broken. So they come in and out continuously under shear deformation. So some of the weakening mechanism, and I'm sure that you have heard about some of these previously, is flash heating. So Professor Jim Rice at Harvard was pioneering in incorporating this idea that under high pressure and slip rate, you can get very high local heating at the contact asperities, and that cause flash weakening in the contact asperities, reducing their strength and allowing the fault to slip at a much lower frictional resistance than it was supposed to be at lower slip rates. So we extended this theory in to granular materials because there are some subtle differences between sliding on a bare rock surface where shearing a gouge of a finite thickness. And the main difference is that the slip rate in a gouge material is distributed across many contacts. So the contact slip rate is actually lower than the imposed slip rate, not like when you slide two bare rock surfaces, the contact slip rate is approximately equal to the imposed slip rate. Furthermore, the stresses, if you have a narrow layer of gouge, then the stresses would probably be uniform across or constant across these contact asperities, whereas in a bare rock surface experiment, the stresses would be distributed across the asperities. So it's a complementary system to the bare rock surface. And the idea was you shear it. We have the viscoplastic formulation that I'm going to describe, but then locally, you can actually estimate the local contact slip rate. You can solve a local diffusion, heat diffusion equation to track the temperature of the contact. And by tracking the temperature of the contact, you can feed back into the contact strength that feeds back into the viscoplastic formulation. So that's one example. The other example is grain breakage. So we can imagine that under high slip rates and pressure and the stress concentration associated with shear band propagation and cracks, then probably bigger particles would have to be fragmented in order to allow further slip. Because if they are too big, then probably they are not easy to move around, but by breaking them, you produce smaller particles that can move around. A third avenue that we have started doing in the last year was to understand the effect of vibration in granular material, and I will focus a little bit more in this presentation on that, but you can think of it that way. If you shear a granular layer, then it dilates. If you vibrate a granular layer, then it tends to compact. So what if you have both of them active together? Then there is a competition between dilation and compaction, and we think this could be relevant to earthquake mechanics in two ways. One, people are currently interested in this phenomena of dynamic triggering, where you have an earthquake happening on a given fault, and eventually, because of the waves traveling from that fault, it can actually set another distant fault into an earthquake, which wasn't supposed to move at that point. But it moved because of the dynamic wave propagation that impacts that fault. Or something that we would like to do is, if we look at the crack or the shear band, so locally we expect to have high frequency oscillations and wave emitted from the crack tip. And these waves would probably cause compaction for the granular material ahead of the crack tip. So we'd like to look into two things, either externally applied vibrations or internally generated vibration in the granular layer. And this is why having a geometry in experiments that allows for dynamic rupture propagation, for example, is important, because in a rotary shear, you don't have a crack. Rotary shear means that you keep sliding upon a certain contact for whatever time you would like to slide. So you wouldn't see these compaction due to wave propagation, for example. So the theory that we are going to use was actually developed by, in the late 90s by James Langer and Michael Falk. It's called the shear transformation zone theory, and they developed it primarily, or in the first place, for bulk metallic glasses, but it's actually a framework to describe plasticity in amorphous materials in general. And granular materials, although they are locally crystalline at the grain level, but globally they are amorphous and disordered. So the main idea of this theory is that in your system, there are fast degrees of freedom and slow degrees of freedom. The fast degrees of freedom are associated with the noisy motion of the particle or the thermal fluctuations of your molecules. So that gives rise to your thermodynamic temperature. But then, eventually, conditions could be right that a bunch of particles would have just a little extra free volume that allows them to rearrange. So this is a much slower motion, but this is what's relevant to plasticity because the rearrangement of the particle causes a configurational change in the fabric of the material, and this reconfiguration is associated with the plastic slip. So this is an example here. You have some particles here that under shear would eventually, because the system is noisy, would have little extra free volume that can flip in the other direction. And this idea was also known by Frank Spiepen in Harvard and others, but maybe in the late 90s it has been casted into a more thermodynamic consistent framework. So the idea here is what we'd really like to focus on is this configurational degrees of freedom because this is what causes the permanent change in the fabric of the granular material and gives rise to the plastic deformation, but we cannot completely ignore this fast degrees of freedom. There is some coupling between the fast and slow degrees of freedom, but this coupling is weak. And more recently, this theory has been formulated within the framework of hard spheres, which is more relevant to granular materials that we are interested in, by introducing an internal state variable called compactivity, which is associated with how you are going to change the volume for each configurational change that you induce into the system. So if you recognize the definition of Gibbs temperature is actually the change of the energy per respect to entropy. So here it's the change in volume with respect to entropy. So one thing that you would like to keep in mind in this, what we call compactivity, is eventually tied to volume changes, and you can think of it loosely as porosity, okay? And then the theory has some kinematics. So this is the master equation for these localized zones at which the shear transformation happens. So you imagine in the very simple formulation of the theory that your shear transformation zones can be aligned or anti-aligned with the degree of the principal stresses, and they can flip from one orientation to another. So you can here postulate a master equation to track the rate of change of the number of STZs oriented in the positive direction and the number of STZs oriented in the negative direction. And how do you write this? Well, using transition state theory, you could have some rate effects. So R plus, this means would operate on the negatively oriented STZs, transforming it into positively oriented STZs, so increasing their number. But then you have some positively oriented STZs that move away into the other direction. So that decreases the number of positive STZs. And then you have a term here that accounts for the creation or annihilation of your STZs. So just even if there is no transition, just because at some location there's this creation of the free volume or this local compaction, which is the destruction of the free volume, you can keep creating or destroying STZs. If you accept this framework, then we can have a kinematic relation for the plastic strain rate, because with each flip of the STZs or each sliding local sliding phenomena, you would produce an increment of the plastic strain rate. And so that would be the rate at which you produce the plastic strain rate. This is a time scale to control this generation rate, and this epsilon node is over n is the magnitude of the plastic strain rate at each increment. So each STZ would produce an incremental plastic strain rate, and this expression will just sum them over all the transition, possible transition in your material. And then you can define an STZ density, which is the total number of these defects relative to the total number of sites or particles you have into your system. You can also, should be an equal sign. You could also define an orientational bias parameter, because as I mentioned, some STZs would be positively oriented, some STZs would be negatively oriented. So you can find what's the orientational bias by defining this is an equal sign. So this is the difference between the plus and minus STZ. And then just for dimensionalization purposes, you can define the non-dimensional compactivity, which is the compactivity divided by a volume scale. And you can define a non-dimensional shear stress by dividing the shear stress over the pressure. And then the theory is driven by thermodynamics. So you could write down the equations of thermodynamics. So this is the first law of thermodynamics, which basically say that you have your conventional external work rate, which is coming from the shear component and the work against pressure. You are also, if we are interested in vibration, then vibration would also provide some energy to the system. And then this energy has to balance with the dissipation or the heat. So that is the heat of the system. That is the thermal energy. And then you have the second law of thermodynamics, which says that the rate of increase of entropy should be non-negative. And based on this idea that we have configurational and kinetic, we have slow and fast degrees of freedom, we can decompose the entropy into entropy associated with the slow degree of freedom and entropy associated with the fast degrees of freedom, and the sum of them has to be greater than or equal to 0. And using the classical argument of thermodynamics, we can write the dissipation inequality, which would constrain how the evolution of the internal state variable and how is it related to the work rate. And then we have another equation related to the kinetic degrees of freedom, from which we can constrain this evolution of entropy. And one thing to just recognize is that, and this is in this paper actually this is 2014, I'm sorry, for more details, but from thermodynamic point of view, you will need to introduce a coupling coefficient. You would just say that this one, in order to satisfy that this inequality has to be positive, this one has to be proportional to this term, and this introduces a coupling coefficient that would play a critical role in our system.
Can I just ask a quick
Sure.
question of clarification about the entropy?
Sure.
So if I remember correctly, it was for Sam Edwards in the 80s.
Exactly.
So it's kind of for a given state, it's the number of equivalent, so the entropy is for a given sort of situation, is the number of equivalent situations.
Can you turn it on?
So I think that you actually can't hear, but it's for the, is it for the recording?
I can hear you
Okay.
properly, don't worry.
Okay. So for the definition of entropy for this system, it's the number of equivalent states that are available to the system, right?
Yeah, to explore a
so-
given volume, that's true.
Right, and so so if you have sort of a mixture of different sizes, it kind of gets more complicated,
Yeah.
right?
We pretend that we suppress this complexity for the moment. And Sam Edwards' approach was actually more related to packing mechanics. So it was purely static approach. So here we actually will have a dynamic component because our system is evolving and being sheared. So one contribution of this approach that was shown by Liu and Langer is that we can carry on this compactivity concept and put it into a dynamic framework that shows the evolution of the system. Mm-hmm. Now, of course, granular material has a distribution of sizes, but we assume for the moment that we are interested in the average size of that distribution. So we have a characteristic grain size that we will put into our system.
So when you defined the compactivity about 3 slides ago, it was dVdSc.
Yeah.
And that's the slow movements. And
Right.
is it because that's the formalism taken from the sort of quasi-static
Right.
investigation? Okay, thanks
Right.
a lot.
Right. Okay, thank you. Okay, so if we go through this, then from the, just to go one slide back, here you can see that in the first law of thermodynamics, this compactivity appears, and we also have this rate of change of the configurational entropy, which we can also postulate that it's a function of the compactivity and the volume. But the one important point is the first law of thermodynamics can constrain the evolution of your compactivity because it has this term, where we postulated that the volume is actually a function of this configurational entropy. So you take the derivative, the time derivative of the volume would have the partial derivative with respect to the configurational entropy, as well as whatever internal degrees of freedom, like the STZ density and the STZ orientational bias. So we can have, from the first law of thermodynamics and some constraint on the form of the coupling coefficient from the second law, we could have an equation of evolution for our compactivities that takes this form. And let me just show you, in order to make it more transparent, what does this mean? So let's imagine first that we don't have vibration. So we only have a sheared system. So in that case, it turns out, it comes out from the thermodynamics that this coupling coefficient would be equal to W, which is something related, it's the dissipation, actually, it's something related to the work rate. So it's something related to the shear stress multiplied by the plastic strain rate over some steady state function that this compactivity would eventually evolve to, because we know from experiments on granular material that you shear the granular layer, it dilates until it reaches a steady state that's consistent with the strain rate that you are applied. And so the evolution of the compactivity in that case reduces to this expression, which basically means that you increase your, by applying external work rate, you increase your compactivity or decrease it until it reaches this chi hat, and then the evolution stops. And this W is, as I mentioned, is proportional to the plastic work rate. So this is the normalized shear stress, and this is the plastic strain rate. The other limit is, let's imagine we don't have external shear, but we are only vibrating the system. Then we would postulate that the system would compact to a new state that's a function of the vibration intensity. So the coupling coefficient would come out from the thermodynamic using this expression, where Y is the energy input by the external vibration, and this is the steady state value of the compactivity for various vibration intensity. And two things here. There were experiments in the 90s from Professor Jaeger at University of Chicago that shows that if you vibrate a column of granular material, then it compacts, and this compaction, compacted volume would decreases as the vibration intensity increases until you actually apply a really high vibration intensity, then the volume gets larger again. So for some range of vibration intensities, your granular material would compact. And this is, of course, something we may experience in our everyday life. And the second thing is that the vibration intensity could be quantified by an acceleration-like quantity, where the vibration intensity is proportional to the amplitude of the wave and the square of its frequency. And then furthermore, if you have friction into the system, then you can actually, so if you have vibration and shear acting together, then you would think that you should have some coupling between these two formula. So this is actually an assumption. This doesn't come from the thermodynamic. This is an assumption of how you combine these two systems together. I would tell you what F is in a moment, but let's imagine F is 0. Then this is how you combine the shear and the vibration. And there's a coupling coefficient here that we found in order to best fit the data. We found that it has to go like this, exponential of minus Q is the inertia number, and rho is the vibration intensity. So what is F? F here is something that we got interested in. It's basically a measure of frictional interaction between the grain or internal dissipation because of the roughness or the angularity of the grains, because I will show some experimental results that shows if you have glass beads versus angular sand, your volume as a function of strain rate actually behaves differently. So what we postulate here is that this F, which is a frictional dissipation, should actually go like if you imagine you have some viscous interaction, then your frictional dissipation should depend on your strain rate, your strain rate, but we found that this cannot continue forever. In fact, eventually, because as you really dilate the system, the number of contacts would decrease, maybe the local strain rate would decrease, so you would have saturation of the system. So that's why you have a hyperbolic change. So at low strain rate, this is actually behaving like a quadratic function, and then it saturates at higher strain rates. So we put that theory, of course, I'm presenting the theory first, but actually we were presented by the experiments first. So this is an experiment that was done in Santa Cruz from Emily Brodsky group, where they have a torsional apparatus where they can shear glass beads, angular sands, different type of granular material, and they can also put an acoustic transducer on their apparatus so they can send pulses. So they can send acoustic vibration, and they wanted to look at how does the volume of the shear band, because they observed that the localization of deformation in the top surface, how does the volume of this layer changes as a function of the dimensionless shear rate. And the dimensionless shear rate, you can imagine it's the inertia number, actually. So the dotted data with the uncertainty bars are the experimental measurements. So what did they observe? So observe that if you have glass beads, which are relatively smooth, they are not ideally smooth, you have a little bit of compaction, maybe invisible at intermediate strain rate. But mostly you don't have dependence of the volume on strain rate, and then as you go to higher and higher inertia number, you get a dilation. Whereas if you look at the blue curve, which is angular sand, there is no vibration yet into the system, and you repeat the experiment, then you get a kind of a dip at intermediate strain rates, and then eventually you get dilation afterwards. So remember, we said vibration could be external or could be internal. So the hypothesis here is that when you shear this granular material, you have internally generated vibration because of particles bumping through each other and trying to go over one another. And this, at intermediate strain rate, maybe the vibration, the internally generated acoustic vibration can overcome the shear-induced dilation tendency, and you get steady-state compaction. But eventually, you shear fast enough, then you recover the dilation again. Now, if you apply acoustic vibration, external vibration, then in the glass beads, you would actually, at very low strain rates, you would actually start with a more compacted sample, because the vibration would cause compaction. So you start with a more compacted sample, but then eventually you dilate monotonically. Becomes more complicated in angular grains. So you started with angular grains with vibration. You started with a more compacted sample, again, because the vibration at low strain rates external vibration would cause the compaction of the system, and then you dilate, but then interact again with this region where the internally generated acoustic vibration is important, and then eventually the shear rate takes over and becomes, you have dilation. So these were the experimental measurements, and then this one is actually, the dotted line here are the predictions of the theory. We can choose parameters for our theory that can fit these experiments, showing this competition between compaction and dilation.
Sorry, quick question.
Sure.
I think that a microphone is needed, but the dimensionless shear rate, can you just define it again?
It's equal to the strain rate multiplied by the inertia time scale. So it's actually the inertia number. So it's gamma dot times tau, where we define tau as the grain size divided by the square root of pressure over rho.
Oh, and so
It's the inertia number.
And so the shaking
This
for all those cases
is the same intensity.
Okay.
So this is just for one intensity of vibration, but different shear rates. All right, so that was quite interesting because of, at least for us, because of the following observation. If you have this non-monotonic, and I will show a slide later, if you have this non-monotonic volume changes in the system, where you can change from compaction to dilation and vice versa, this leads to a non-monotonic change in rheology. So people doing granular mechanics, computational mechanics, DEM, etc., they would always have this nice curve of the coefficient of friction, macroscopic, or the steady state shear stress as a function of inertia number, and it would be almost flat at low strain rates, and then it would show strain rate strengthening, right? So that's consistent with the idea of dilation. But if you have this non-monotonic dilation and compaction, then you actually have a region where the steady state stress or the steady state macroscopic friction becomes rate weakening. And when you have rate weakening, you can have the possibility of stick-slip. Because basically what happens in rate weakening material is that you shear it, its strength goes down, so you shear it, it can actually it goes faster. So you have this feedback mechanism that can allow for the growth of instabilities. And eventually other mechanisms would come and stop this when you say the elastic energy or something like that. So we did validate this hypothesis by testing cases where we have this non-monotonic kind of behavior for the volume as a function of strain rate. So this is at different strain rates and the pressure. This curve shows the shear stress as a function of shear strain. And you can see here, if we don't have this non-monotonic behavior, say we have a frictionless grains, then you get steady sliding. So you shear the system up to a certain point, then you get strain softening, and then you get steady sliding. Whereas if you have a non-monotonic rheology due to the compaction and dilation, then you get this kind of stick slip. I will talk about this later. Another prediction of the model is the effect of your externally generated vibration would actually depend on the pressure. So you could have a system that's originally in stick slip because it's a frictional system, and then you apply acoustic vibration, and then your vibration amplitude would increase, amplify. Or if you repeat that experiment at a different pressure, then you could actually amplify it a little bit, and then the vibration will take over and reduces the stick slip amplitude. Eventually, you can get steady sliding. So the interaction, and in this paper, we have a kind of phase diagram that shows the interaction between pressure and vibration, and where can you get amplified stick slip and where you can get suppressed stick slip. But this amplification of stick slip means that you have vibration, you can transfer a system that was more quiescent into a more vigorous system because you have triggered it. Or in this case, you could have a system that has vibration, but then you kill the system by vibration. You eventually make the system goes into steady sliding. And then if you take out the vibration, then the system can recover into its original state or not, depending on the internal state of the system. So we know that, okay, we can have vibration of different amplitudes. It's not only, or vibration of different intensities. It's not only a single intensity. So if we play with our theory and predict the behavior for different vibration intensities, so this is no vibration, just the frictional grains being sheared. So you have this dip, and then you have a dilation. Now, if you have a given vibration intensity, then you start with a more compacted case. You increase the vibration intensity, you start with a more and more compacted case. Eventually, of course, you cannot compact the material beyond a certain level. So these curves here converge, but the interesting thing is, as you increase the vibration intensity, the non-monotonicity in the curve becomes diminished. So at a higher vibration intensity, although you start with a very compacted specimen, but eventually what you experience is almost monotonic dilation. So in that case, you wouldn't expect Stickslip, whereas in these cases, you would expect Stickslip. Because these are non-monotonic, this is monotonic with dilation, then it will just be steady sliding. So what is the implications of this? Well, one interesting implication for this is, if you consider a system without vibration, it will give you Stickslip phenomena like this. Now, if you keep increasing the vibration intensity, at low vibration intensity, you get what we call slip advancing. So the vibration would try to trigger the first strain softening a little bit earlier, because the vibration would try to disorganize the system and loosen it or fluidize it. So you get this Stickslip, and then you get this slip advance, which means that the first slip event happens earlier than without vibration. And then you keep increasing the system, the vibration intensity, you keep getting slip advancing until some point. But what happens later is that, if you can see here, the slip here is pretty abrupt, happening over a short, sorry, this is the shear strain. So this is happening at very short external strain application. So it's almost instantaneous. So that's the slip in the Stickslip phase. But if you increase the vibration intensity, your slip accumulation happens on progressively slower scales. So as you keep the vibration, as you increase the vibration intensity, you make your slip slower and slower. So you accumulate maybe the same amount of plastic slip, so you can get the same amount of earthquakes, but it's happening over longer periods of time. And eventually, of course, if we really go to higher vibration intensity, we get the monotonic change, and then we will just have steady sliding eventually. But this phenomena, we can call it slow slip, and it has been observed. There are many theories why slow slip happen. Basically, slow slip means you might accumulate a large amount of slip, comparable, say, to magnitude 7 earthquake, but then instead of having this slip happening in few seconds or in a minute, like in normal earthquake, you have it happening over days, sometimes weeks, okay? So it's not creep, because its velocities are actually higher than creeps, orders of magnitude higher than creep, but they're not seismic events either, because their velocities are lower than the shear wave speed. So why would that happen? There are different theories related to fluid propagation, dilatant hardening, and stuff like this. But what we postulated here is, maybe if you have a source of vibration nearby, continuous source of vibration, and they do have continuous sources of vibration, like tremors, tides, and stuff like this, acting over an extended period of time, then that can trigger slow slip accumulation. I think I will have to run fast, but well, all what I have shown so far, even with Stickslip, was just assuming a 1D model for our granular layer. What happens if we would like to look at strain localization? So I'll show just one slide here in the simplified model before going to the more complicated model. In order to trigger strain localization, there are different ways to do this. And I know many of you might have heard from Professor Jim Rice about the flash heating and thermal weakening mechanisms that can trigger these instabilities. Here we look at a complementary mechanism where the disorder can also trigger strain localization. So if you have a dense granular material and you have a region of increased porosity and you shear that region, then the region of increased porosity would accumulate plastic slip, more plastic slip than the surrounding domain. So what will happen here in our terminology is that your compactivity goes up, but strain rate would also go up. But the compactivity rate is proportional to the strain rate, so there's a feedback loop here, which tends to, if you have a small perturbation in your compactivity, that tends to make it grow and localize. And here is an example. This is a space-time plot. So this is in the direction of time. This is across the width of the specimen. And what you are seeing here are maps for the compactivity as you keep shearing the system. So this is as time progressing. And you can see here that we start with almost uniform compactivity, except with an intermediate region that has a little bit of increase in compactivity. Eventually, this region would accumulate most of the compactivity and localizes. And if you have friction in the system, then you can get stick slip. And when you have shear bands, actually the stick slip will happen only within the shear band. Now, if you have vibration, then vibration tend to fluidize the system and will tend to delocalize the shear band. So eventually it can localize, but because of vibration inducing plastic deformation everywhere, it would eventually be delocalized. Although this is here in a frictional system and vibration, this is appear to be more localized, but actually the background compactivity here is comparable to this magnitude. One more thing I would like to show you here before moving into the continuum part is if you look at these stress-strain curves, this is a comparison between the stress-slip curve without vibration and this is with vibration. So you can see that the vibration tends to soften the material and reduces its peak strength. But more interestingly, if we look at this strain rate in the plot of shear stress versus strain rate, this strain rate actually on the yellow curve here corresponds to rate strengthening. So it wasn't supposed to produce a stick slip because a rate strengthening material becomes stronger with increasing rate, so it shouldn't be unstable. But what happens is because this system localizes, then the actual strain rate within the shear band is higher than the imposed strain rate. The actual strain rate within the shear band is 1 or 2 orders of magnitude higher. So you're actually effectively on that branch within the strain rate, within the shear band. So this branch is a rate weakening branch. And this is why you get stick slip, although the imposed strain rate should put you in the steady sliding. So we can take this formulation and put it in a more consistent way to continuum mechanics. We transfer our plastic strain rate into a flow rule, which would basically be the same one as the one-dimensional. So it depends on how many STZs you have. It depends on the rate of transition of STZs. And it's also coaxial with the deviatoric shear stress. And then you can also write the internal variable evolution. Now I took, just for simplicity, I took the vibration and friction effect out. So again, this chi dot is a function of the work rate, and it depends on the effective pressure, and it should go into a steady state function. And from thermodynamic arguments, you would find that we will have to have also a diffusion-like term to compete with the strain localization, which was good also for numerical purposes. And we can implement this plasticity formulation in Moose. It's a finite element software from Idaho, in which we can now do some numerical experiment for, say, you have a strip, and you start with maybe a uniformly dense material, except in a localized region where you perturb this density, and then you shear it under pressure. And I would like to show you some of the predictions of the model. So for example, you can predict the shear stress evolution as a function of displacement, and associated with these different points, you can look at the evolution of shear bands. So first, you get this shear band growing, and what is appear at the radial shear, and then the radial shear Riddell shear grows and eventually hit the boundary, so you get a boundary shear, and it also bifurcates into what we call a Y shear. So eventually, to accommodate large slips, the Y shear becomes most effective. The Y shear is this one. And do we see something like this? So this is, this is from Logan, 1987. This is a schematic of the shear patterns we see in fault zones. So you have the through-going Y shear, you have a boundary shear, you have a Riddell shear 1, Riddell shear 2, and X band. We didn't get everything here because, of course, it's a function of the initial condition that you get and the heterogeneity of the system, but at least we get the Riddell shear and the boundary shear and the Y shear, and somehow we get also this X band. Another prediction of the model is if you start with a loose material, then you get a ductile-like behavior without strain localization, where it's much easier for the material to distribute plasticity everywhere because it's already highly disordered than to localize it. But if you start with a dense material and you shear it, then you get dilatant shear bands and you get strain softening. And of course, I cannot finish the presentation. I have a couple of more slides, but I have to incorporate water here, right? So we did some very recent simulation where we can add the pore pressure variation evolution equation coupled with our viscoplasticity. So this is the Laplacian of the pore pressure. This is a pore pressure rate. This is the dilatancy effect. And if we need, we can also put thermal pressurization, but we just suppress it for now. And you can see here, if we have a dry material, it would be stronger. If we have a saturated but drained condition, the effective pressure would be lower because the pore pressure wouldn't change, so it would be weaker. But then if you shear the material and allow dilation, then you get what we call dilatant hardening, where the material actually, the strength of the material increases with respect to the one which has undrained pore pressure condition, and the strain localization pattern also changes. So to close this, in the next 5 minutes, I would like to show you something that, okay, we have done this modeling of the fault zone. At least we have a model that can localize complex shear localization patterns, and we can look eventually into poromechanics. But what we'd like to do is to couple that with the elastic rock in order to be able to investigate the effect of these small-scale granular mechanics implications on elastodynamics. And this is a daunting task because since the medium now is nonlinear due to the existence of the shear zone, we can only solve it with finite element of finite difference. And if we want to localize a shear band within an elastic material in elastodynamics, so we have wave propagation, we need to use very fine mesh, and we need probably to use this mesh everywhere in the system to avoid artificial reflection. So this is a very computationally challenging task, and what we like to do is to come up with a coupling mechanism that takes advantage of having an elastic bulk and that the nonlinearities are localized within a narrow zone, okay? So just wait, okay. So this is what we are going to do now. Hopefully we couldn't recruit that guy, but we had talented graduate student. So there is a very interesting method that was developed by James Rice and Philippe Guibel called the spectral boundary integral formulation, and it was actually expanded significantly by Nadia Lapusta and Jim Rice in 2000 to allow simulation of long-time sequence of earthquakes. And the method is built on the idea that if you have a linear elastic bulk, then you can use superposition of fundamental solutions. So you can get the Green's function, and you can convolve, you can only discretize the fault, forget about the bulk, and write down an integral equation for the shear stress at any point as a function of the initial shear stress and a space-time convolution that connects the deformation at one point to deformation at another point through the Green's function representation. And this is just the radiation damping. But this method only works for linear media, but it has a very good advantage. If your medium is homogeneous and the fault is planar, then you actually know the analytical representation of the Green's function. And so you can transform your space-time convolution into the Fourier domain. So you change this non-local formulation, integral formulation, to be a local formulation in the Fourier domain, and thus the method becomes very computationally efficient. But it's only that computationally efficient if you have a linear, of course, it has to have a linear medium, but if the medium is homogeneous and the fault is planar, then it's very efficient. And then Lapusta showed a very interesting way to truncate even the convolution integrals to make sure that we don't keep storing all the history that we need from time 0 to the current time, but only the effective part. So this allowed for modeling of earthquake cycles. But we cannot use Lapusta et al. Formulation here because our medium has nonlinearities, but remember they are local, right? And our faults are non-planar, whether you have a rough fault or you have a non-planar shear band. So even if the medium is linear elastic, the non-planarity of the faults will make it not efficient. You don't know the Green's function in an analytical form. But finite element and finite difference everywhere is just computationally prohibitive. And we can use dynamic adaptive mesh refinement, but it's a completely different game. And it's even for the data structure and stuff like this. We might eventually need to do that, but here are the challenges that we have. To connect the scales is very problematic, okay? So we tried to get to that guy, but again, the graduate student was very talented, so we didn't do that. So what actually ended up is there is an underused formulation for this integral boundary equation. You can actually formulate the integral boundary equation for each half space independently, and that's what Gubel and Rice did. But then after that, they joined the solution at the fault plane using continuity of traction. Here, we will join the solution in the fault, not on the fault plane, but we will join the solution on the boundaries of the nonlinear domain. So here is an example, just to illustrate that the method works. Here is a fault that's governed by slip weakening friction, and here is a compliant layer. So you embed the fault in a layer that has a lower Young's modulus than the remaining bulk. We cannot use Lapusta et al. Formulation for that way because the medium is heterogeneous. But what we can do is, since the medium is still linear elastic outside whatever this region is, we can introduce a virtual interface here and a virtual interface. These interfaces are not real. They are just virtual for computational purposes. And we can take this virtual strip outside. And what we can do is we can solve within that strip using finite difference of finite element. We impose the traction on the virtual boundary where we invoke the spectral boundary method. So we can take the traction from here, solve for displacement on the upper and lower boundaries using the spectral boundary integral equation in the Fourier domain, which makes it very efficient, and then impose the displacement back on the strip and march forward the solution. So it's similar to the domain decomposition approach that we use in fluid structure interaction, but here we are using it for elastodynamics. And we tested the problem. We thought that this could induce artificial reflection because we are taking it very close to the fault. So classically absorbing boundary condition will be far away in order to avoid any artificial reflection. But because the spectral boundary equation is exact, we don't have any artificial reflection. So what I'm showing here is a comparison of what if we solve the whole domain using finite difference versus this hybrid method, and the solution, this is the slip along the fault plane for different times, and the solution looks very promising. And also we compare the solution for the displacement at the virtual interface, and it's very promising. So just This is not an absorbing boundary condition. It's an exact truncation for the wave field. It works for dynamic, quasi-dynamic, and static simulation because the boundary integral is exact in these limits. It's also, people have tried coupling finite element with boundary element, but if you do that in the time domain, it's very challenging because your stiffness matrix becomes non-local and not banded. So you have a populated stiffness matrix. And then the spectral approach makes convolution very promising. So this is the conclusions. And what I would like to say is now we have the ability to hopefully embed our high-resolution fault physics into elastodynamic model and couple them to allow the propagation and initiation of complex shear bands. We can also start looking at competition between dilatancy and thermal pressurization, which people find difficulty in exploring experimentally, and there are not much models in that. And of course, if we are trying to do predictive modeling, then we need uncertainty quantification. And I will close here thanking my students, Konik, Sitara, and Chauma, and my funding agencies. So thank you very much, and sorry if I kept you a long time.
There's the mic back. Thank you very much. We have time for a few questions.
I have a question regarding when you develop a continuum level model based on the discrete model. Do you introduce any, I guess you introduce a land scale in the continuum model.
Right.
What is this land scale and how you determine the land scale?
Yeah, so actually, first, the STZ theory is a continuum model that homogenizes the discrete physics underlying the granular mechanics. So if you see here, the short answer is that this length scale is proportional to the grain size. So how we come up with this gradient term is that when the thermodynamic representation, we assume that there's also a flux for energy associated with the configurational degrees of freedom, and then the flux has to be gradient of the potential. So this leaves us with a tensor that we don't know yet. So it cannot be constrained by thermodynamics, except that it has to be positive. So since this tensor has the units of meters squared per second, we think that the fundamental length scale in our problem is the grain size. So we can think of the disorder being transferred over length scales equal to the grain size by, say, collisions and stuff like this. And the time scale, we have two time scales that we can use. We have the STZ transition time scale or the inverse of the inelastic strain rate. So we chose here to use that as the inelastic strain rate. So the length scale is coming from the grain size, and the time scale for diffusion is coming from the strain rate. But it's a very complicated question in any non-local gradient-based theory. What is the origin of that length scale physically? I know I probably went far over time, so I...
So what prompted you to choose that particular way to couple the fine scale and the coarse scale? That seems to kind of originate from the earthquake modeling community specifically, as opposed to things like bridging scales, bridging domain techniques, things developed, for example, for continuum atomistic coupling.
Right.
So the more general literature in that regard.
Exactly. This is an excellent question. So in many cases, like quasi-continuum method, for example, and other techniques, would work very well if you don't have wave propagation or phonons, if you don't have high-frequency waves, because you couple this between a coarse mesh and the fine mesh, and then you probably end up with problems propagating the high-frequency waves into the coarser mesh. So what prompted us to do this coupling is that the spectral integral, first, the fault geometry is almost quasi-linear. Like it could be rough, but it could be encapsulated in a tube. And the nonlinearities are localized, so we don't have nonlinearities everywhere in the system, or heterogeneities. If the heterogeneities are far away from the system, they probably will not affect the rupture propagation. So for that purpose, we thought that first, the boundary integral is an exact or transparent way to propagate wave propagation. So we even think that we can put a discrete element model in that mesh, and then the high frequency waves, if we have just the boundary integral discretized well enough, it can propagate these high frequency waves and it wouldn't be a problem. So first, it's a transparent way to propagate the full spectrum of the wave field, but then it's also, because we have this infrastructure in the earthquake community of doing the spectral boundary integral equation, at least me, because I also was like co-advised by Nadia, so we learn how to use the convolutions and do it in the Fourier domain. So we think it would be a more easier way for the earthquake community to use this coupling than in quasi-continuum or something. But the fundamental difference is we have a transparent condition for the wave propagation.
I understand the value of the elegant explanation of what can happen in the granular material.
Right.
And you pointed this very well, that there are many different granular materials. But I still cannot capture practical applications of what you're talking about.
Okay.
And earthquake happens and it does whatever it does. You cannot
Right.
intervene very much over there.
Yes.
So what are possible applications?
Okay. So first, if I put on my hat of structural engineer, I would agree with you, right? As engineers, we would like to prevent failure, right? So what we care about is the wave motion at the site and the nonlinear site amplification effects, etc. But in the earthquake community, we still have challenges in understanding the processes that govern the strength evolution that controls the rupture propagation. And that's more than critical because we have cases like Tohoku earthquakes where people relying on historical seismicity would have expected that the earthquake would be maybe magnitude 8 point something. But what happens is that, or 7.8. So the magnitude of that earthquake was magnitude 9. And the reason why is that people thought that there's a zone there's an area in the subduction zone that's not capable of sustaining dynamic ruptures based on understanding the behavior at low slip rates. But what happens is when the earthquake comes with high slip rates, it actually heats up the fluids in that area and causes thermal weakening. And the area that wasn't supposed to be ruptured actually accumulated most of the slip. So the magnitude changes from 7.8 to magnitude 9, and instead of not triggering a tsunami, it triggered a large-scale tsunami. So there's actual implications for seismic hazard if we can quantify and characterize the potential for failure in these granular materials. But on even a more practical scale, maybe in landslides, in soil mechanics, in running these grains on transmission belts in factories to understand how the stucking happen, and then how can you say apply an external vibration to get it unstuck, how to control this, control of phenomena that's associated with local instabilities and friction. I think this work can have some practical implication. But the driving force behind developing these models are basically to understand failure and deformation in earthquakes.
Right, yeah, to be close.
Okay.
I will ask you